Hello everyone, this is Athota Rathan Babu, working as an assistant professor in the Department of Aeronautical Engineering, and I'm dealing with the course Computational Aerodynamics. And in today's topic, we will see finite volume method for the 1D diffusion equation. So we have seen in the previous module basically what is finite volume method, and we have already given some insights, like already have seen some basic aspects of 1D equation, and similarly we have seen how we perform it for 1D flow, 2D flow and 3D flow, how these things will differ in detail. We will all, like we have seen. Now for the 1D flow we will see the finite volume formulation for the diffusion equation. Okay, so to recap the things, so we have taken, let us take, we have taken the element P. For the element P, so we have these as the west face, and here we have the east face. So this is for 1D element. For the 1D element, we have west, we have east, we have point of interest P. Fine. So this is what we have seen for the 1D. For the 2D, what we have seen, so again we draw a point of interest P. Top we have north, here side we have west, here side we have east, here we have south. Okay, so what do we have? Here we have point of interest P, here we have west, here we have east. So similarly we have point of interest P, here we have west, here we have east, here we have north, here we have south. That is, this is for 2D. Next we have 3D. For the 3D, what do we have? So we have taken again the point of interest P. Top we have north, bottom we have south, we have west, we have east, here we have front, here we have back. So here what are the dependencies? Point of interest P is depending on west, east. Here point of interest P is depending on west, east, north, south. Here point of interest P is depending on west, east, north, south, front, back. Okay, so this is what we have. So we have seen clearly that so when we take the point of interest P, that depends on two factors or two values for the 1D flow. For the 2D flow, it depends on four variables, which is north, south, east, west. For the 3D, it depends on north and south, east, west, front, back. Total 6. Okay, so 2, 4 and 6. Fine. Now let us clearly see how do we apply. This is for 1D flow, which is for diffusion equation. Okay, so let us write. So this is point of interest P. This is our base. So next, here this is west. Here this is east. Okay, so when we actually do the line integral, so we get the line dl. So when you do integral of dl, so we'll get L. So let's say this is 1D. So since it is cross section, so when you do this area, so we'll get LA. Okay, so what happens? So the area and the west face we will take as AW. Okay, next the area at the east face, we will take it as AE. Okay, so this is what we have. So the area at the east face, so we will take it as this as area of interest, let's say AE. So here this one it has this one it has AW, this one it is as AE. Okay, so when we do this line integral, let's say this integral, so let's say dou by dou x of u, as we are doing area integral in between a w to AE. What happens actually? So that would give us, so u at west face, sorry, east face into AE minus u at west face into west. So this is what we have. Okay, so here what we are doing, so here we are actually interested with these two things first. So in order to get east west, but the major thing is we need to see for the point of interest P. So this term, so what we are doing, so we are integrating in such a way that from west to point of interest P plus here from P to E, which is dou u by dou x. Okay, so this is what we have to do. Fine. Similarly, so if you take these as a constant, okay, so mu, so already we discussed what is the value of mu. So the mu value is taken constant when you consider it as a eddy diffusivity, or let's say we take it as eddy diffusivity, or let's say molecular diffusivity, then we cannot take it as constant. When you take this one as only laminar flow, so mu we can take it as constant. When you take the flow as turbulent, when you can take it as mu t. Okay, so where the viscosity will vary because of eddies. Fine. So this is what we have. So this is for 1D flow. Okay, so when we see full form, so what do we have? So we will have integral of west east is equal to so mu d by dx of u is equal to west node to point of interest P. Okay, to d by dx of mu into d by dx of u plus point of interest P to east node d by dx of mu to du by dx. So this is what we have. Fine. For this, what we have done, so initially, like when you do the area integral, so you can take it as dA. Okay, so when you do this integral first, what we have, so mu at w minus mu at p will get. Okay, so into, so what do we have? u of w into a of w minus u of p minus into a of p is what we have. Now how do we get mu of p? So this thing also we need to know. How do we get mu of w? This thing also we need to know. So this is the rough estimation or the rough summary of this integral. Okay, so this is what how do we do for the 1D diffusion equation. So similarly, this 1D diffusion equation, so we can apply it for the temperature option. Basically, so let us take the 1D element. So this is the rod. This is point A. So this is point B. Okay, so this is a rod. So for this we have diffusion equation. So d by dx of let's say alpha into d by dx of temperature T equal to 0. So this is what we have. Now, so there is one thing. So since A is wall and B is wall, so what we do, let us actually write down this 1D element thing, finite variable formulation for this rod. So A, this one, this is B. Okay, so here actually we have to mark the points. 1, this has 2, let's say. This one has 3. This one has 4. Okay, so what are the things we have? So point 1 is having the neighboring points A and the neighboring points 2. So for this we'll get one set of equation. Okay, next point 2 is having the neighboring points. This has 1, this has 2, sorry 3. So this will be other set of equation. Okay, so this is 1. Next, for the point 3, we have this as 2, we have this as 4. This will be other set of equation. Next, for the point 4, here you have 3, here we have B. This here we have one set of equation. Okay, so here what we have 1, we have 2, we have 3, we have 4. So basically there are 4 equations which we will derive. So with these 4 equations, so basically the concept of point of interest P, so this is the point of interest P which we have for the equation 1. So this will be the west node and this will be the east node. Okay, so this is what we have. Similarly for the second equation, so this will be point of interest P and this will be the west node and this will be the east node. Fine. So similarly here this will be the point of interest P, so this will be the west node, this will be the east node. Similarly for this equation, this will be the point of interest P, this will be the west node and this will be the east node. So when we derive these equations from 1, 2, 3, 4, we will write down for each element. So what we do is like we apply the boundary condition. So what is the value of temperature at A? Let us take it as 300 Kelvin. So T at B, let us take it as 400 Kelvin. What is alpha? So since the area of cross section, so what is happening? So here the assumptions we will take. Area at A is equal to area at 1 is equal to area at 2 is equal to area at 3 is equal to area at 4 is equal to area at B. So which we can take direct it as A. Okay, so what we are doing is like when we are approaching the problem of diffusion, So for the finite volume method, so you can take how many elements? Here I have taken sample 4. So 4 elements. You can take 5 elements. You can take 10 elements, 20, 30, 40. The procedure is same. So what is the point of interest P? So that we have to mark it. So if we take A, let us take this is the point of interest A. So there is no west node for the A. So therefore A of W is equal to 0. Okay. So there are no terms on the west of the A for the face A. Similarly, for the B, so there is no east face. A is equal to 0. So this is what we have for the west, for the east. Okay. So A, the remaining terms, we have areas A of A, A1, A2, A3, A4, AB. So which is equal to A. When we take all the areas subsequently are equal to the same areas. Fine. So with this, this is the approach what we see for the 1D diffusion equation. When you take the boundary conditions, T of A is equal to 300 Kelvin and T of B is equal to 400 Kelvin. So with these conditions, we will actually see the formulation. But now, actually for the finite volume method, there are two approaches. One is like defining the, let's say you have the control volume first. First we draw the control volume. For the control volume, we will mark the cells. Okay. For this, actually, what we have done? So first we have drawn the control volume. For the control volumes, we have marked initially what is the centroid. There is one more approach where first we will define the nodes. Okay. Then surrounding to these nodes, so whatever the points we have, for these points, so the midsection of these 2 points, let's say this is the midsection here, this is the midsection. Let us take this point of interest P. This is 1, 2, 3, 4, 5, 6. We will take the midpoint between P and 1. So this one. We will take the midpoint between P and 2. This one. We will take the midpoint between P and 3. Let's say this one. We will take the midpoint between P and 4. This is one. We will take the midpoint between P and 5. This one. We will take the midpoint between P and 6. This one. We will draw. Sorry. The imaginary volume. So this is one approach. So first approach is where we define the control volume and the cells. Then we will locate the centroids. And the second approach what we have is we will first draw the nodes. So for the corresponding neighbor nodes at the midsection of these neighboring nodes, so we will mark the points and we will add the locus of those all midsections. Then we will frame or we will get a face. Okay. So this corresponding type is the another type of approach. In general, people actually perform this first approach compared to the second approach. Now, when we see the basic difference between finite volume and finite difference method, so here for the finite difference method, so we actually focus on the vertex, or let's say this is called this the grid. Okay. Now for finite volume method, we will see at the centroid. What the difference we saw? So when we see the Taylor series of expansion, f of x plus delta x is equal to f of x plus dou by dou x of f into delta x divided by 1 factorial plus dou square f by dou x square to delta x square divided by 2 factorial plus so on. So we will actually neglect some higher order terms, so truncation error terms in the finite difference method. But for finite volume method, what we do is like you have conservativeness. Okay, so there are no truncated error terms. So whatever the flux going here, it will go here. So internal fluxes will get cancelled. So the global flux, whatever flow enters, that flow will leaves. Okay, so this is the procedure what we have in the finite volume method. So for the finite volume method, so basically the stability and the conservativeness, the consistency, and the global conservativeness are satisfied. Like more amount of stability actually has to be evaluated, and it will be consistent with the finite volume method. If you see finite difference method, so conditionally stable aspect has to be seen, and the errors, so the truncation errors, so order of accuracy, these things we need to estimate actually. If not, so it actually it will lead to errors. So the errors basically you have different types. So we have dissipative errors, we have dispersive errors, and we have round off errors, and we have the numerical errors. So these errors we have already like seen. Okay, so when you see the finite volume method, so what we have seen, finite volume method, there is the conservativeness where the flux internally which leaves, which again gains. So globally in overall, finite volume method has more amount of applications. So whatever the complex grid you take, finite volume method can be done. So whatever the simple grid you take, finite volume method can be done. Unstructured mesh, finite volume method can be done. Structured mesh, finite volume method can be done. But whereas for the finite difference method, unstructured mesh you cannot do. Why? Because the location of the grid points and the index notation is difficult. So for a given grid point, so many number of interconnectivity nodes are there. It is complex. So only for simple problems you can apply finite difference method. For complex problems you cannot apply finite difference method. Whereas finite volume method is a global method which is suitable for all kind of applications. In the next module we will see basically in detail so the numerical problem and the tutorial for the finite volume method. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.